All right, we are back, and today we're talking about complex numbers, and the complex number system. All right, so what is a complex number? A complex number is a number that has the following form. So the form for a complex number is a plus bi, where a is real because it doesn't have an I attached to it. And the b is imaginary because it has an I attached to it. Alright? The I squared is equal to the imaginary unit. And let's go ahead and move forward to get into the operations of complex numbers. Oh, I didn't mean to put that there. Let's see here. So we have, when adding complex numbers, you add with the real. So in this case, A and C are the real, and they form that section. B plus DI, those are the imaginary components. All they did was factor out the I. That's the same thing as saying BI plus DI. Alright? But this will make a whole lot more sense whenever we start doing examples. These operations is just theory stuff that you can read, general concepts that you can read. But watch how easy it is when you're doing an example. All right, so for part A, identify it says adding and subtracting complex numbers. First thing I want you to do is identify the values that are the real values. If you said 3 and 5 are real, you're absolutely correct. So just perform the operation that separates. We have 3 plus 5. That's the real part. And then, so we'll just toss that in a parenthesis. We have 3 plus 5. And then we have the imaginary part. Well, let's toss the imaginary in a different set of parentheses. We have negative 2i plus negative 4i. And whenever you simplify those two, you have 8 for the real component minus 6i for the imaginary component. That's it. That's all you have to do. Make sure you write it in complex standard form, which is a plus bi, where you have the real part first, followed by the imaginary part. And you clearly see the separation. Let's do the same example and use subtracting. Let's go to part B. So we have 3 minus 5. And then so I'm just going to write above it the real. And then I'm going to put the imaginary. Negative 2i minus negative 4i. For the real, I have negative 2. For the imaginary, I have positive 2i. Yeah, I feel like writing real and imaginary is better than drawing those arrows. So let me take that Ricky move of arrows off my screen there. Yeah, and I'm going to go back and toss in real and imaginary. So we have real, imaginary. Okay. And do the same process for multiplication. You treat multiplying complex numbers, you treat it just like you would multiply any binomial by distribution. So we have 3 minus 2i times 5 minus 4i. So I'm going to take 3 times the entire times the entire second parenthesis. And then I'll follow that with, I'll take negative 2i times the entire second parenthesis group. And my next step is to distribute. Distributing, we have 3 times 5 gives us 15 minus 12i. So that takes care of the first parenthesis. Now I'm going to move over. I have negative 10i plus 8i squared. Combine like terms and simplify. We have 15 minus 22i plus 8, and I squared from the very first sheet is equal to negative 1. So we have 15 minus 8 is 7 for the real part, and negative 22i for the imaginary part. All right. Let's keep rolling. Complex conjugates. Okay, this might sound like a big thing, but all it's saying is to take the opposite sign of the imaginary part. That is it. The opposite sign of the imaginary part. So here we have z is the name of this complex number. They just gave it a name. They called it z. So then they said, what is z bar? Z bar is simply saying what is the conjugate of z. So all you do is write out your exact same complex number, except this time you will write the opposite sign of the imaginary part. That is it. That is all it's saying do. Okay? Now, let's jump into some example with this. And 3 minus 2y. All right, quick example. We have z equals 3 minus 2i. So find z bar. What is z bar? Oh, z bar? Oh, that's all I gotta do? Man, z bar is equal to 3 plus 2i. Because I took the opposite sign of the imaginary part. Alright? This little theorem says when you multiply a complex number by its conjugate, then it will always be a squared plus b squared. And that's a shortcut that you want to keep in mind. Or you can multiply it out the long way just to verify. And when you multiply it out the long way, you're just going to go through this whole process. Okay, so you have z is a plus bi times z bar, which is a minus bi. And you go through all this multiplication. You have a squared minus a bi plus a bi minus b squared times I squared. And that would give us a squared minus b squared times negative 1, which results into a squared plus b squared. You can either do it this long way, or remember that whenever you multiply conjugates and it's original, it'll always be a squared plus b squared. And this is very necessary whenever we're simplifying rational complex numbers. All right, it says write this rational complex number in standard form. Find the quotient. All right, so here, in order to do so, this is something that you want to have in mind. Oh, didn't mean to do that. Let's take it back. All right, you want to have to write a quotient in standard form. You multiply the numerator and denominator by the conjugate of the numerator. Multiply the numerator and denominator. Oh, by the conjugate of the denominator. I am tripping. My apologies. By the conjugate of the denominator. By the conjugate of the denominator. All right. Now let's hop into our example. So we have solution. 3 minus 2i over 5 minus 4i. So I'm going to multiply the numerator and denominator by the conjugate of the denominator. And that will give us and the numerator, you have no choice. You got to multiply it out the long way. So you have 3 times 5 plus 4i. Then negative 2i times negative 2i times 5 plus 4i. And in the denominator, use the theorem that you just learned, because you have a product of the original times its conjugate. So that would be a squared. So we have 5 squared plus b squared. And you can put that in easily. And then distribute in the numerator, simplifying the denominator. So we have 15 plus 12i minus 10i minus 8i squared plus, well, all over 41. All right. Next step, simplify the numerator. You have 15 plus 2i minus 8 times negative 1. Because I squared again is negative 1. Equal, we have 15 plus 8 gives us 23 plus 2i over 41. Though this answer is correct, it's not in standard form because your components are not readily distinguishable. So you separate your answer. 23 over 41 for the real part plus 2i over 41 for the imaginary part. You want to always be able to identify the real part and the imaginary part. Now, a few quick little examples. If z equals 3 minus I and w equals 2 minus 5i, write each in standard form. So this says z over w this is, you would do this exactly how we did in the previous example. Multiply the numerator and denominator by the conjugate of the denominator. And you have 3 minus I times 2 minus 5I all over 2 squared minus, well, plus negative 5 squared. I went ahead and skipped a step because I'm only going to have a little bit of space. We have 6 minus 15I minus 2I plus 6I squared all over, I didn't mean to say 6I squared, plus 5I squared all over 41, and that will give us 1 minus 17I over 41, and that equals that equals 1 over 41 minus 17I over 41. Part B, that's the same thing as saying the conjugate of Z plus the conjugate of W. Take the conjugates, add the real with the real, the imaginary with the imaginary. And then part C, you have Z plus its conjugate. Whenever you're doing the Z plus its conjugate, so I'm just going to write some answers up here, and you just try to fill in how to get those answers using the knowledge that you've obtained. Okay. And we have 3 plus I plus 2 plus 5I. That will give us 5 plus 6I. Okay. And we're almost home. We're almost home. Important theorem right here. The conjugate of a real number. The conjugate of a real number is the real number itself. The conjugate of a real number is the real number of itself. So if we say Z equals 12, and we want to know, and then I'm just going to toss the word example right there. Example Z equals 12, what is Z bar? Well, 12 is a real number. You do not see an I present. Therefore, Z bar is equal to 12. And if you use the definition from earlier, the conjugate of complex numbers simply tells you to take the opposite sign of the imaginary part. And there's no imaginary part present there. Okay? And the powers of I, basically, as long as you know how to go old school and use remainders with respect to 4, this will be very easy. All right, because it'll repeat. I to the first will be 1, I squared, so on, once it gets to if there is no remainder, that's the same thing as saying I to the 4th. So let's say we have this example, I to the 33rd. We want to know what that is. So the trick is take 33 and divide it by 4. So I'm going to take 33 and divide it by 4 and find out what the remainder is. Alright, the only thing I'm concerned with is the remainder. 4 will go into 33 8 times. That gives me a remainder of 1. So that tells me that I to the 33 is the same thing as I to the first. So that is I. We'll do the same thing for 82. Take 82 and divide it by 4. Find out what the remainder is. 4 goes into 82 20 times. We have a remainder of 2. So that's telling me that I to the 82nd is the same thing as I squared, which equals -1. And we use the number 4 because it repeats this cycle every fourth term. It's going to keep doing the exact same thing. Okay. Now, principal square root. Suppose you take the square root of a negative number. Taking the square root of the negative number, that's the same thing as saying, I like to add in my little stuff. This is the same thing as saying -1 times that number, the square root of -1 times that number. And from earlier, we said, well, square root of -1 is I, and that leaves us with times the square root of that number. So we'll make this fairly easy. Square root of -1 is I. In this next example, we have -9 is the same thing as saying -1 times 9. So we have square root of -1 is I times the square root of 9 is 3. So this final answer is 3i. Same process throughout. Square root of -1 times 18, since we're dealing with square roots. 18 has a perfect square that will go into it. So we have this is I square root 18. Perfect square that goes into 18 is 9. And it does it. It goes into 18 twice. So that leaves us with 3i. The square root of 9 is 3. And the 2 cannot be simplified. I didn't mean to change the screen that quickly. I apologize. All right. Solve the equation in the complex number system. All right, we're in the complex number system now. So, note in the complex number system, no real solution is not an option in the complex number system. Okay, so square root method still applies. So taking the square root of each side, x equal plus or minus 3. All right, we'll move this x squared plus 25 on over. So that gives us x squared equal -25. Apply the square root method. Applying the square root method, we have square root of x squared equals plus or minus square root of -25. So that gives us x equals plus or minus. The square root of 25 is 5, but it was negative, so we know we have our imaginary component. We're almost there. Quadratic formula. Last time I tried to drop a few tunes on y'all, you know what I'm saying? Even though I don't claim to be a singer, but I dropped a note. I told you you'll need to remember the quadratic formula. But remember that in the complex number system, I told you that the no real solution is not an option in the complex number system. It's because whenever we get down to the quadratic formula, if the discriminant is less than 0, meaning negative, then there exists two complex solutions, because we are in the complex number system. Okay? Example, solve the equation in the complex number system. We have x squared minus 6x plus 13. We have a quadratic equation in front of us. I'm going to go ahead and plug this information into my discriminant. So that we have b is negative 6. So I have negative 6 squared minus 4 times a, which is 1, and times c, which is 13. My discriminant here is, we have 36 minus 42. So my discriminant is, that's 52. And that makes my discriminant negative 16. So that lets me know I have two complex solutions. And everything else is like before. To find the solutions, plug it into the quadratic formula. And just to toss quadratic formula up top, x equal negative b plus or minus square root b squared minus 4ac. We're just gonna put it all over 2a. Yeah. All right. Now, plugging in the remainder information to find your solutions. All right. X equal opposite of b. B is negative 6. So we'll have opposite of negative 6 plus or minus the square root of my discriminant. And that will be all over 2a. So we have 6 plus or minus square root of 16 is 4, but it was negative, all over 2. 6 divided by 2 is 3, plus or minus 4 divided by 2 is 2. All right. Finally, it says determine the character of the solutions of each equation. In order to determine the character is determined by the discriminant. And that is b squared minus 4ac. All right, so for each of these, I take b squared minus 4ac and down equals 3 squared minus 4 times a, which is 2, times c, which is 1. That's 9 minus 8 equal 1. So since this is positive, the character of the equation, because your discriminant is positive, character equals 2 unique real solutions. right? And you do the same thing every time. All right, you have b squared minus 4ac, and that is negative 2 squared minus 4 times 5 times 4. That tells me that I have 4 minus 80. My discriminant is negative, so the character is 2 complex or imaginary solutions. And for the final example of the day, we have 16 minus 16. My discriminant equals 0. So my character is, if you say my discriminant equals 0, so my character is one unique solution, you are on it. All right, that's 1.3 complex numbers in the and quadratic